Yeah, let me start by thanking the organizers for this very nice conference, and of course also to give me the opportunity to speak to you today. I'll talk indeed about Jordanian twisted string theories and Jordanian twisted spin chains. It will be based on work that I did over the last few years with Ricardo Borsato in Santiago de Compostela, and then also work that appeared today on the archive with my student Adrien Molin, who is also here. And he will also have a poster tomorrow. So, because I'll be talking in these 30 minutes about these two different topics, I hope I can still give you some interesting facts about them. But any more discussion, if you're interested, I revert to the poster. I'm sure that Adrien will be happy to discuss it. So, yes, the motivation of my work stems basically from looking at deformations of the AdS-CFT correspondence and using integrability to study those things. In particular, there is, in fact, a very nice, simple algebraic realization of deformations of the integrable framework, of the integrable hop framework, which is known as Drinfeld twists. So I'll explain what they are during the talk. And basically what they do is like twisting your universal R matrix in some nice way such that the properties of the Hopf algebra will be preserved. So in contrast to Eddie's talk of this morning, we will still have like Yang-Baxter equations and stuff like that that is valid here. What I'm interested in is applying these type of things to the case that we all know and love very well. Which is the AdS5 CFT4 correspondence in the planar limit, where we have this nice triangular structure of theories, where on the one hand side we have a string theory propagating in AdS5 S5 spacetime. Then on the other hand we have this highly symmetrical gauge theory, which is NS4 superangles. And then underlying to that, as we all know, is some PSU2,2/4 invariant spin chain that encodes the integrability of these two models. And so, as you know, they're extremely symmetric. So we have PSU2,2/4, so we have some conformal subgroup. So the gauge theory is some CFT. We also have maximal SUSY, and we have integrability realized through Yangian. So the question that I want to ask in my work is, can we sort of twist this triangle with these Drinfeld twists, and in that way study symmetry breaking effects in theories like quantum gravity and QFT models, where we still have exact techniques in principle from integrability. And now there is some nice conjecture about the modification of the integrability framework by these Drinfeld twists, which was formulated in 2015 by Stijn van Tongeren. Which is that, at least at the string theory side, we have a deformation of this model, which is called, by the very creative name, a Yang-Baxter deformation, and maybe we should actually call it a classical Yang-Baxter deformation, where, so as I said, the target space in which the string gets deformed, in which the string is propagating, it will be deformed. And it is done, the deformation is done by some object, which is some classical type of R matrix. And then in the other corners, we have this Drinfeld twisting of the quasi-triangular Hopf algebra of the spin chain. And on the gauge theory side, the idea is, or the conjecture is that the field product of the gauge theory gets deformed through some star product, which is also realized through a Drinfeld twist. And in this talk, specifically, I will talk about Jordanian deformations, which are a part of Yang-Baxter deformations, and I will focus on the string and on the spin chain side. Okay, so yeah, the first part will be on the string world sheet, where I'll talk about the Lax and the S matrix, and then I will go to the spin chain. So first, let me tell you what the definition is of a Yang-Baxter string sigma model. So there are some particular integrable deformation of a two-dimensional sigma model, so the world sheet theory, which has some isometry group G, which in the case of AdS5 S5 is PSU2,2/4. And it has this very particular action, so we know precisely what the two-dimensional action is. The precise form doesn't really matter here, but I just display it. It is in principle just some deformation of a Green-Schwarz superstring. And the deformation is governed by this object eta and r. So eta is just a deformation parameter, and r is a particular operator. And then I should also tell you that G, which will come up later also in the talk, G is a collection of fields, some group-valued collection of the fields of the worldsheet. But so this, the important bit here is this operator, this classical R matrix, satisfying a bunch of properties. So in particular, it satisfies a classical version of the Yang-Baxter equation, which is this line here, and it's also antisymmetric with respect to the metric of the supergroup. And also some unimodularity condition, and those conditions combined will ensure you that the two-dimensional worldsheet theory is still classically integrable, so I can write down a lax connection for you. And also the resulting background in which a string is propagating will be still a solution of the type 2B supergravity equations of motion. So it will be some complicated solution, but it will still be a solution. And now all of these sort of properties, what is interesting is that they correspond to Drinfeld twists, classical Drinfeld twists, which are connected to the identity. So I have this object curly f, that is the Drinfeld twist, and it's connected to the identity through this R matrix in here. And interestingly, in the case of PSU224, we have a whole plethora of possible solutions to these conditions. And these have been classified in these two papers here. So there's a huge family of possible integrable deformations that you could study in principle. Some of them are actually quite well known to you. So there's specific Yang-Baxter deformations which give you the backgrounds that have been studied a lot, so like the Lunin-Maldacena background. Also Schrödinger spacetimes are realized as Yang-Baxter deformations. And then there's a whole bunch of other possibilities which haven't been studied. And I'll try to go quick, but basically they're sort of distinguished by, in three main classes, and they're distinguished by the subalgebra, which is the image of this R matrix that is minimally two-dimensional, so it's spanned by at least two generators of PSU224, so T1 and T2. And then you have these three classes where either the subalgebra is abelian and the generators are Cartan generators, so they are diagonalizable. In that case, we say that they are called, well, we call them diagonal TST transformations. At the level of the worldsheet, you can actually understand them as TST, so T-duality, shift T-duality transformations over this commuting subalgebra of isometries, this abelian subalgebra. And in the second case, we still have an abelian subalgebra, but then one of the generators may not be Cartan. This is, of course, possible in PSU224. In that case, we will call it a non-diagonal TST. Basically, the classical Drinfeld twist that is associated to it is non-diagonalizable. And the final class that I want to study are called Jordanian deformations, where the subalgebra is non-abelian. It is some type of SL2R subalgebra in PSU224, where the T1 generator is the Cartan of SL2R, the H, and the other generator is the raising or the lowering operator or generator of SL2R. And what is nice about them is that they have a classical Drinfeld twist, which is diagonalizable, and that sort of, I will not be able to really tell you why that's nice, but basically it should allow a nice treatment of the integrability methods. So just to complete a bit the picture, so I told you you have this Lunin-Maldacena, which is some diagonal TST, and we also have other cases. What do we know at the gauge theory side? So we can take these two generators, these commuting generators, to be commuting generators in the isometry group of the sphere in SO6. So then we're not deforming the AdS space, and we will have a marginal deformation of NS4. The other possibility is that you take abelian generators where one leg is in the AdS space in SO2,4 and the other leg is in SO6, or you have two legs in SO2,4, and in that case you'll be deforming the space-time symmetries of the gauge theory, and that introduces to you some non-commutativity between the fields. So that relates to these non-commutative star products that I mentioned earlier. And then for this SL2R subalgebra, the Jordanian case, it's really totally unexplored terrain, what happens there. But also here, there should be some non-commutativity. Okay, so now let me just focus on very particular Jordanian deformations. As I said, there's many possibilities, but there's one that I think is interesting, which is one where we have the Cartan generator of SL2R, which take this form in terms of the conformal generator. So here we have the dilatation operator and then some boost generator. And then the root of SL2R is some null momentum combination of the momentum generators that we have here. And this is a case that will give you a constant dilaton. So in the other classes of Jordanian deformations, you will always find non-constant dilatons up to this nice structure and possible generalizations of this one. So that's the one I will be focusing on, and that is also the one that has been studied from various angles before. Now, what is nice about this one as well is that it has an interesting symmetry structure. So the residual symmetries of the sigma model and the AdS in the AdS5 space I've listed down here. So there's like 5 generators that remain after this deformation. And as you can convince yourself, there's some SL2R subgroup and 2 central elements. And this SL2R subgroup is also called a Schrödinger algebra, which is relevant for studying non-relativistic CFTs. So in particular, we don't have like a relativistic SO2,4 CFT anymore, but we still have some sort of non-relativistic version of that, which is surviving here. So we have this boosted dilatation operator, which will define for you some non-relativistic scaling symmetry. And then we have these other guys, which will define for you the descendants of the non-relativistic operators and also a state operator map. Okay, so then what will be important throughout the talk is the existence of the Cartan subalgebra in AdS, in this AdS space. We have, as in the usual case, we will have 3 Cartan generators, but they look very different to usual. So we have always the E generator, this raising operator that will be present, and it will be defining for you some charge, which is some null momentum M, and this M will continue to appear throughout the talk. Then we also have some rotation, this J12, which will define some spin in AdS, and then we can choose 2 elements of SL2R as a third Cartan element. We either have a time-like generator, which is this guy, which will define an energy for you, and then finally I also have a radial generator, which will define this non-relativistic scaling. And they are related through the state operator map in this case. Okay, and then you also can write down the type 2b supergravity solution in terms of those isometry relations. So now that I defined the model, let me talk a bit about the possible integral structure of these cases, and I'll start with the S-matrix formulation of this guy. I won't have a lot of time to give you all the technical details about this thing, but basically the point is that because we're severely deforming the space and we're left only with a specific Cartan subalgebra, we cannot do the usual identification of the asymptotic states that will be scattering in the, that will scatter through each other. And you'll have to do another type of gauge fixing, so a specific light cone gauge fixing that will change your structure. But let me just mention that the solution that you take to do the gauge fixing will be this particular type of, you can take the simplest possible solution will be of this form, where we turn on some energy as well as this null momentum M and an angular momentum in the sphere. We leave the spin of AdS, we can turn it off, and then we will find some, the Virasoro constraint will relate these charges through each other in this particular way, which is, if you're used to it, is just a deformation basically of the BMN or BPS operator where the energy is equal to the angular momentum. So at some large values of the angular momentum, we'll just have some combination here, a deformation of that with this momentum charge. Okay, and so we use this energy to do the gauge fixing. As I said, you do a different type of gauge fixing. You'll find some different worldsheet Hamiltonian than in the usual case. So you will have some symmetries of that gauge fixed theory, which will not be the usual PSU2/2 squared, but there will be some different symmetries. And in fact, the symmetries that are surviving, they contain this H and this E that are defining the Jordanian deformation. So in principle, you could think of like also twisting the S matrix of this gauged fixed theory through some type of Drinfeld twist, as I said here. But so this is sort of like the expectation of what should happen. But if we would start to like shut up and calculate and see what the S matrix actually is, we run into some strange features. So we take this gauge, we find the perturbative Hamiltonian, we look at its expansion in the asymptotic states, where we have this cubic Hamiltonian contributing as well as higher order terms. And then we will find that we'll get some very nasty dispersion relations for the excitations, so they take this form. They're non-relativistic. And that means that you cannot just use normal kinematic rules for them. And in fact, you'll find that this cubic part of the Hamiltonian will not just disappear because of this non-relativistic dispersion relations, but it will actually contribute physically to the scattering of the S matrix. And we find in particular two nasty production processes that involve massive asymptotic particles. And as you, I'm sure, very well know, this is quite not nice because it means we have inelastic scattering at tree level, which is violating the usual axioms of S matrix integrability, or in principle, it's just jeopardizing the methods that are based on factorized S matrices. And it's also like sort of questioning what is happening to the Drinfeld twisting, because usually the S matrix in the sigma model is the first signature that you have this R matrix appearing. Yes. Higher order in what? Yes, yeah. I mean, I would expect that I already at tree level I should have no production process, right? Yeah, well, maybe I can talk about that later. Okay. Oh, okay, I see. Yeah, okay. Well, yeah, no, I'm not, I don't think so. I don't have a compelling intuitive answer for now, but it would be quite surprising to me, actually. But, okay. So, yeah, anyway, what I just want to say about this is that it's like a sign of that the asymptotic Hilbert space is kind of weird, and maybe particle number is not a good conservation quantity, conserved quantity. And it's also something that we see signs of in the spin chain language. Yeah, so all in all, I think, well, so it's the S matrix formulation is a bit unclear, but what the connection to the Drinfeld twist is kind of nice in terms of the lax integrability, which I'll just briefly discuss right now. So we have these two classical lax descriptions for these Yang-Baxter deformations and also for Jordanian ones, where we have sort of two pictures. On the one side, we have a deformed interaction picture where the Hamiltonian is deformed through this eta R object, but the fields of the sigma model are still periodic. And then we can derive some lax connection of that, which depends on this eta. And on the other side, we have an undeformed interaction picture, but the fields, the deformation gets completely transferred to a twist in the fields themselves. So here we have some twisted strings propagating in some undeformed spacetime, and here we have some closed strings in a deformed spacetime. And the mapping between the two is done precisely by some type of classical Drinfeld twist, which is this F here. In fact, you can show that if you look at the sigma model monotomy, the generator of the conserved charges, it is classically Drinfeld twisted in the following way. So you take this monotomy object, which is this path ordered exponential of your deformed lax connection, and you see that you can sort of strip off the deformed part in terms of like some overall twisting of the undeformed monotomy object here through this guy F that carries the deformation. We found in this paper in 21 here that it is indeed of this classical Drinfeld twist form, so it's connected to the identity again with the same object. And then for the abelian or the Jordanian deformations, we were able to write down explicit expressions. And for those that are familiar with it, in the abelian case, we really get some abelian Drinfeld twist, which is also known as a Drinfeld-Reshetkin twist. And then for the Jordanian twist, we get a structure that is also very similar to known Jordanian Drinfeld twists. So yeah, that brings up a sort of first connection between the string theory and the spin chain, where the string is twisted with this type of object. So now let me go to the spin chain formulation of these models through this Drinfeld twist. So now I can be a bit more precise about what they mean. So as I said, I'll be looking at this minimal Jordanian model that is non-trivial in an SL2R sector of PSU224. And in that case, the relevant spin chain is the Heisenberg XXX spin chain in a non-compact representation of spin -1/2. So it has some Yangian SL2R related, realized through some co-products, and has some R matrix. And in this, for this particular case, the R matrix in some representation takes this form here, where we have the generators of SL2R acting on physical spin chain sites through some differential operators in some continuous parameter Z. And so the wave function is also some depends continuously on this parameter. Now, you can Drinfeld twist this theory, and that specifically what you have to do in order to preserve the co-cycle condition is you need to have some object that satisfies this. What you need to do to preserve the quasi-triangular Hopf algebra or the R matrix integrability is that you need to have an object F that satisfies this co-cycle condition. And in the case of the Jordanian Drinfeld twists was done by people like Coolidge and probably also many others. The form of this Drinfeld twist has this exponential and also this log term that also similarly was appearing here at the classical site. Where we have this, again, this Cartan of SL2R and this raising operator of SL2R, and now my deformation parameter will be psi, which is some real deformation parameter. And then you can show that you can actually twist the Hopf algebra, so you get some twisted coproduct, some twisted R matrix, and you'll just have normal Yang-Baxter equations and RTT relations, etc. Now, importantly for analyzing this type of model, and especially the spectrum, is looking at the symmetries that are the residual symmetries of this system. And for the level 0 or the SL2R generators, you'll find that the only manifest symmetry is realized again through this E operator, which we also had at the sigma model side. It's also always a residual symmetry also there. And we labeled that guy with charge M, and here it is some operator, M hat. And yeah, we want to sort of, or if we want to study the spectrum of this model, we want to organize it in terms of this an eigenbasis of this residual symmetry. Now we looked also, to do that we used some general formulas, or we wrote down some general formulas for the twisted monotomy matrix after doing such a Drinfeld twist. So in the usual case, we have this nice product of our R matrices over some auxiliary space, and then and the physical space as well. And then after the Drinfeld twisting, this gets this nice structure where we have some overall similarity transformation of your physical spin chain, but then also some Drinfeld twisted additional actions on the usual monotomy matrix, really in the sort of the same analogy as we had here for the sigma model monotomy. Oh, sorry, that should be U. Yeah, I had set everywhere and I changed it to U. Yeah. So that's a U. And then here we see this very general structure appearing, which in the case of the Jordanian model takes this particular form. And what I want you to focus on is simply that the guy that is first acting on the physical space, which is called this beta A, will be realized through the symmetry operator delta, so the co-product of E on the physical spin chain sides. And then on the other side, we have sort of the opposite version. Okay. Then I totally won't have time to discuss this slide really in detail, but let me just say that we also gave some explicit formulas for the twisted boundary conditions of this Drinfeld twisted spin chain. So in general, the expectation of those guys is that you have this quasi-triangular Hopf algebra that is twisted and defines for you some deformed Hamiltonian with some periodic boundary conditions on the level on the side 1 generators. And the expectation is that you can map this structure similar as in the sigma model. You can map it to an undeformed Hopf algebra with an undeformed Hamiltonian and twisted boundary conditions that are realized through some symmetry action. And I'll just revert to the poster of Adrian for that, but basically we have some gluing procedure where we find the twisted boundary conditions given again by the same object beta that also appeared in the twisted monotomy, which is for the Jordanian case here realized in terms of the residual symmetries. And so for SL2R, we wrote down the specific boundary conditions for the E, H, and F generator that you see here. So then we used those two things, the twisted monotomy and the twisted boundary conditions, to study or to initiate the study of the spectral problem for these models. And we did it in two extreme regimes. So on one side, we looked at the thermodynamic large length limit. And on the other side, we had a small length spin chain with just two sides. And in the thermodynamic limit, we use this connection to Landau-Lifshitz theories. So we start with some undeformed interaction Hamiltonian, which you can take the continuum limit of, as was done by people in the room. And you can look at like the field theory version of this Heisenberg Hamiltonian, and you'll find it to be this type of guy. So for the people that know, it's just like going to some coherent states representation of the spin chain. And we did this same continuum limit at the level of the twisted boundary conditions to see what the fields of this sigma model have to be, and then you'll again find some realization in terms of this M residual symmetry, which is really like the same thing as the co-product of the E operator at the spin chain site. And then we studied minimal energy solutions to this Hamiltonian, and we found that are subjected to these twisted boundary conditions. And then we find an energy that precisely matches the deformed part of the sigma model Virasoro constraint that we had earlier. So here we had this deformation of the BPS operator with this M charge, and here we see exactly the same thing happening. So that's quite nice. We have this from two different perspectives. On one side, it came from the spin chain Drinfeld twisting, and on the other side, it came from studying the solutions of the equations of motion of the sigma model. So I'll have to wrap up a bit faster now, but we also looked at the small chain guy, and here we used the twisted monotomy matrix. In particular, it was important for us to put the physical spin chain in an eigenbasis of this M hat, rather than an eigenbasis of a Fock space states of the Cartan generator of SL2R, where the functional wave function will have this particular form. And then we studied the spectrum of the twisted transfer matrix, which after the Drinfeld twist has these extra combinations here. Let me just mention that you're not really able to do normal algebraic beta ansatz, because there won't be any like non-trivial pseudo vacuum with a non-zero M charge on which you can start the ABA procedure. But what we did was just like, as a first step to looking at the spectrum, is just like do a straight eigenvalue calculation problem of this twisted transfer matrix, rather than using some integrability methods. So that will be, because we're working in this non-compact representation of SL2R, it will become some differential problem that we sort of solved with type of Frobenius methods in some sort of perturbative, in a perturbative way, and the solution has this form. And for us, it was important that here we can show that the spectrum of this transfer matrix really gets deformed if you're looking at a spin chain that is in an eigenstate that has non-zero momentum charge, in the same way as we had also for in the continuum limits, where if m was 0, you would find an undeformed spectrum. But in non-zero m sectors, you do get a deformation. And this is sort of in contrast to what several people have been doing over the years in this case, where if you would organize a spectrum in terms of Fock space states, you would get sort of an undeformed spectrum, because essentially the charge sector will be 0. So yeah, I'm running a little bit over time, but I'll just conclude right now. So I talked to you about Jordanian strings and Jordanian spin chains, where we had on the string theory side this nice classical Lex integrability framework, where we have the two formulations of deformed or twisted, where we had signatures of classical Drinfeld twists. And I didn't mention, but that also allowed us to do some classical spectral curve computations on this particular point-like solution that I mentioned. We had some weird particle production processes in there that we don't really understand, involving massive asymptotic states. Yeah, it would be interesting to also, so here it's clear sort of that we should work in some type of basis of this root generator, an eigenbasis of this root generator, rather than some discrete particle number like of a type of basis. So it would be interesting to understand that better and get another notion of this S-matrix integrability in this sense. Then for Drinfeld twisted change, we had some general formulas for the twisted monotomy and the boundary conditions, which in the Jordanian model were in terms of this symmetry operator, and then we looked at the spectral problem, had a match with the string ground state, and also had a non-trivial deformation in the short chain, spin chain. What I didn't mention is that there's some part of the spectrum that we don't really are capturing, so it's not clear how the magnons are realized in the deformation, or at least in a continuous way. And for that, we believe that studying this in a non-perturbative framework in the deformation parameter and also at all lengths of the spin chain will probably help. We also did a short initial study of the Q functions, and having a full analytic structure of that will probably also give some insights to the full spectral, well, very likely give insights to the full spectral problem of these cases. And then in particular, it would be quite interesting to take these large J corrections from there and match them with the string theory semi-classical data. So yeah, I hope I sort of convinced you that there's some nice work still to be done for this Drinfeld twisted AdS5 correspondence. We're sort of starting to uncover a bit about the spin chain. What is still widely open is what happens at the gauge theory side. And then I think it would be extremely interesting to understand. But with that, yeah, I'll thank you. Sorry for going over time.
Thank you for the nice talk. Are there any questions? Thank
you. Could you go back one slide? I wanted to ask, could you go back one slide? Yeah, so here you introduce these two twists. One is off diagonal, the other one is diagonal. So it looks in many ways similar to what we studied with Kostya and Monica, but also your twist is different because you have this diagonal part. So I wanted to ask, if you look at the non-diagonal part, would you introduce an arbitrary parameter in front of this off-diagonal component? Would it make any sense from a string theory point of view, from Drinfeld twist algebraic construction? Or it has to be equal to 1?
Yeah, I think I mean, it will also sort of, so it came from the same object. So if I'm changing something here, I'll also change some stuff here. And well, yeah, basically it's just a rescaling of the deformation parameter. But yeah, so there was no like two type of different twists. There's just one twist, this guy here. And it's because of like the opposite action that the R matrix has, that it sort of looks different after it passed through the R matrix. So that's why it's like has this different type of structure.
Cool, yeah.
Just to understand, Natesh, could you explain in basic terms what is the delta of diagonal element which you just looked?
So
What type of operator is it?
this here?
And this
Just
twist on the next to the last slide, which Fyodor asked you to show. This
Here?
one. Yeah, what is the delta of H? What type of beast is it?
So this is just a co-product of H. So I'm here in the length 2. So I just like H1 plus H2.
In more basic terms?
Even more basic terms. Well, just a cartan of SL2R on the full length 2 spin chain. The action of that on the spin chain. Yeah, just a physical space. Yeah, yeah. So yeah, and in particular, it's an operator in this case. So here we're not in this the eigenbasis of delta H, but here we're in a different eigenbasis, and so it will be some non-trivial operator.
Any further questions? Hey, Arkady? Oh, there.
Some of these examples have supersymmetry, right?
Yeah.
TST, but some not?
Yeah, yeah.
So which one?
The one that we've been studying has 12 supercharges. Weird number because we're destroying the Poincare subalgebra. But yeah, so this one has 12, but you can also, I mean, really supersymmetry it doesn't really play a role here. You could add some additional TSTs. You would have to go to a bigger subsector of PSU2,2/4, but yeah, I think the same sort of things will go through.
One last question by Roger.
All these deformations are unitary, then the theory stays unitary. What's the?
So I think it depends on how you look at it. There are some non-diagonalizable sectors, probably, which we don't completely understand. But yeah, at this level, I don't really have a problem with the unitary or non-unitary thing.
Would it make sense to study some complex parameters which you introduce, like, for example, those who lead to fishnet theory were useful to some.
Maybe
some interesting limits which would bring some.
Yeah, that could be
integrable models.
Yeah, I don't know, but yeah, maybe yeah. Well, you could connect to the compact representations maybe if you go to the complexified algebra, but yeah, we didn't look at this.
Okay.
Okay, then let's thank Sibylle again.